limits at infinity. So what are limits at infinity? So we've talked about limiting to a certain number a, but for infinity nothing really changes, but we can just assume that x tends to a really big number. So if we keep on increasing number, we eventually reach the infinite point. So if we denote this, we can write limit x tends to infinite. So when x is infinitely large for a function f of x, we can actually estimate its value. So you might think it's quite impossible because we are actually putting a hypothetical number like infinity into the equation. But no, it is actually possible by some extent. So let's actually consider a case for rational functions or polynomials. Let's see the polynomial 3x square plus 5 divided by 2x square plus 7. Now I'll give you a certain set of rules which you have to apply. Suppose we have to find this value of this function at infinity when x tends to infinity. So when we see these are two polynomials, numerator is a polynomial and denominator is a polynomial, and what is the degree of this polynomial? The degree is 2 because 2 is the highest power of this polynomial, and for denominator 2 is the highest power of that. So both of these degree is 2. So when the degrees are equal, we can say that divide the numerator and denominator by the highest power of x. The lower degree terms vanish. So what this means is that pretty much all these lower degree terms vanish, and we just can write 3 by 2 simply, as 3 is the coefficient of the highest degree. So and in the denominator 2 is the coefficient of the highest degree. So we can simply write 3 by 2. This is a rule. When degrees are equal, we can only consider the coefficients of the highest degrees. So in the next example, suppose the degree of the numerator is greater than that of the denominator. Suppose the degree of the numerator is greater than that of the denominator. Okay. In this case, 3 is the degree of the numerator because it's x cube plus 1. In the polynomial in the denominator, 2 is the degree of that polynomial. So 3 is the higher degree. So the numerator degree is higher than the denominator. And for these examples, when the denominator degree is less than that of numerator, the answer would be infinity. Now we can't actually proclaim this as the answer, but we just write the result as infinite. So when x tends to infinite for a polynomial rational function where the degree of the numerator is greater than that of the denominator, the answer is infinite. And when x tends to infinity for a rational function where the degree of numerator is less than that of denominator, as the next case, x plus 5 divided by x square plus 1. Here the denominator degree is 2, numerator degree is 1. So denominator degree is greater. So the answer of this would be 0. So when x tends to infinite for a rational function where denominator's degree is greater than that of numerator, the answer is 0. So we need to know these standard results. When the degrees are equal, only the coefficients of the highest degree terms matter. So 3 by 2. Here, when the numerator degree is higher than the denominator, answer is infinite. And when the numerator degree is less than that of denominator, the answer is 0. This was for the case of rational functions. And with these limits of infinity, we have two special results. You have to by heart them. Limit x tends to infinite when 1 by x, that would equal to 0. Or another result, x tends to infinite for 1 by x square, that is also 0. If we think about it, if we put infinite in the denominator, 1 divided by infinite, 1 is such an insignificant number to infinity that the answer is very close to 0. So when x tends to 0, when x tends to infinite, the function tends to 0. So it's pretty clear and logical. So we have to study these two results and these three rules when rational functions and infinites clash. I'll give you an example. Let's do this example and actually understand better. Limit x tends to infinity, 2x square plus 3x plus 1 divided by x square minus 4. Now I'll tell you how this rule came. Before actually just applying the rule, if we actually just apply the rule, these two degrees are equal because both of these degrees are 2. So the answer would be 2 by 1 because 2 is the coefficient here, 1 is the coefficient here. So the answer would be 2. So we know the answer is 2, but I'll tell you how we actually got to that rule and why it matters to not actually do it in the exam. So suppose we take x square out of this. We take x square out of that. So we get 2 plus 3. We took 1x. We have to divide one more x. And we take both x's from 1. And from the denominator we do the same. X square 1 minus 4 divided by x square. Cancel these because we can. And then we apply this limit directly. If we apply that limit, we get 2 plus 3 by infinity plus 1 by infinite square divided by 1 minus 4 by infinite square. I know infinite square doesn't make sense, but let's just cope with it for now. So we know 1 by infinity was 0. So what would be 3 by infinity? It was also going to be 0 because this 3 and 1 and 2, everything under infinity is really insignificant to infinity. So anything, whenever the infinite symbol is in the denominator, the answer would be 0. So here this 3 by infinite will evaluate to 0. So 2 plus 0 plus 1 by infinite square. Infinite square doesn't make sense, but infinity is already big. Infinite squared will be even more bigger. But even though it doesn't make logical sense, we will just take that as 0 itself. And 1 minus 4 by infinite square. 4 is really insignificant to the infinity. So the answer would be 0. So 2 plus 0 which is equal to 2 divided by 1 minus 0, 1. So the answer will be 2. So we got the same result actually by solving, but if we have an MCQ or something in the exam and we see the 2 degrees are equal, we just apply the significant terms. So for here, significant coefficients are 2 and here it's 1. So the answer would be 2. So we can either get the answer like this using this results or get the answer by solving it and actually logically finding out how we got to. I recommend using the rules, but if you're comfortable with this, do that.